Hello! In my backyard today. Let me make sure it's recording. Is it really recording? Yes, it is. Oh, okay. This is my third time trying to do this particular video, and so we're just gonna hope the third time's a charm today. We are working on the midsection of Module 5 out of Exploring Creation with Physical Science, 3rd edition. And I apologize, the first video for this module said that it was covering the first half of the chapter, and yet again I have underestimated the length of these chapters. I really need to look ahead, and so I'm just not going to tell you anymore like how much of this I'm going to get to. I'm going to just go until, as far as I can on this video, and then I'll do another one because I'm positive I will not finish it today for this. So anyways, so with that aside, I want to first of all point out to you that in your textbook, which I'd love for you to go get right now, go get your textbook, go get your student notebook, and get a pencil, and make this an interactive thing and not just like watching it like you're checked out on Netflix or something. This is you're gonna learn this and memorize it so much better if you actually are moving around. And so if you can actually make this a hands-on process with me and get your book out, that would it's really going to help you and dedicate this to memory better. So in your book, go ahead and pause me and go get your book. And now that you've got your book, I'm going to turn and, oh, that's my ducks. They're going crazy. Really? So we've got in the appendix the most wonderful and amazing table you've ever seen in your life, and it is page 533, and it is on the back side of the periodic table. So go find that, and it will tell you all the secrets of the world, or at least of the periodic table, and tell you when you're looking at these symbols what they all actually stand for, which is so helpful and important. And then flip to page 159 to this handy dandy little table. Sorry, the ducks have decided it is time to splash around in their pool. This table 5.4 has prefixes for naming molecular compounds. And so it's got the mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. That is so helpful because I don't know about you, but I see tetra, I don't think 4 all the time. Seriously. Some people just really need attention. I'm sorry, the ducks are really going crazy. So, so when you know where those two are, you've got all the tools you need to decode these formulas. So we're going to start out with the formula P2O5. What is that? All right, well, let's figure it out together. First of all, we have the P, which I looked it up on one of the first few times that I recorded this. And the P, as I recall, I'm going to double check to make sure I'm right. Yep, is phosphorus. So we've got phosphorus right here. And then we're going to see, oh, it's got a subscript. So 2 on the table 5.4 on page 159. These are those pages if you need it. Is first, the 2 is di. So we're going to make it a di, and you can lowercase that p. Diphosphorus. And then for the second element, you're going to not only change its prefix if it has a number, but either way, you will always change its suffix. So this goes from oxygen, which we know O is, to whatever 5 is going to be. Anybody know? Think of the Pentagon. Pentagon has 5 sides, like the building. So we have penta, instead of oxygen, we're going to make it oxide. you can see that. So pentaoxide. So we have diphosphorus pentaoxide. And this is the two elements in this compound. And this is how many atoms of oxygen, how many atoms of phosphorus. Okay, so if we were drawing this out, we would know there would be 2 of the phosphorus and 1, 2, 3, 4, 5 of the oxygen. They'd be a different color. Okay, just for illustration purposes. All right, let's do another one. SeF6. All right, so Se, if you look in the back, will be selenium. I only know this because I've made this video over and over. And the F stands for fluorine. Well, fluorine gets the "ide" suffix and its own special prefix. So looking at table 5.4, 6 is hexa. So we've got hexa, fluor, which is UOR, ide. Get the "ide" in there so that we know that we're dealing with ions here. All right, so an ionic compound, that's how you know that. An anion, there it is. As you did with the anion and the ionic compounds. There we go, I'm just reading that. All right, so that's the one way. So if you've got the formula and how you come up with the name, what if they give you the name and you got to come up with a formula? Well, we got this. Bring it. All right, so what we're going to do is we're going to take the example on page 125 in the student notebook. And it says, what is the chemical formula for dinitrogen pentoxide? Well, we are so ready for this. We got nitrogen is an N. You can look it up in the back table if you need. Dinitrogen means there's 2 of them, right? And then we've got pentoxide. The oxide just means it's oxygen and it's the second element in this compound. And pent means 5. So this is how we would do the formula if they were giving us, they gave us just the name of the formula and we needed to write it out. What if it was dinitrogen tetraoxide? Well, what would we do with that? Well, as you might recall, tetra, it's just, we're going to just picture 4 neon tetras. Those fish, the 4 of them. There's always going to be 4 of them together, and they're never going to die. So we're going to remember tetra is 4. Okay, that's the only weird one in my opinion. Mono's 1. Di, yeah, it's a little weird, but we can kind of remember like a bicycle, di, bi, 2. Okay, 3, tricycle, easy. 5, penta, like the pentagon. You might remember from geometry, hexa 6, hepta 7, octa, like an octopus 8, nona for 9, and deca for 10. Those to me are a little more forthright, but tetra, neon tetras, always 4 of them, okay? So that's how we go the other direction. Now we're going to tackle the types of reactions, and there are 5 in this, but I only drew out 4 of them. So you can see my fancy schmancy darlings here. I actually made these out of what do you call them, pipe cleaners, and my son, who is injured, was super amazingly helpfully trying to help clean so well as he hobbled around on one foot that he threw away all my my little demonstration circles I made to do this. So you have drawings, and that's okay because I have a clean house thanks to my son. So I am not upset. All right, so we've got synthesis and decomposition, single replacement, and double replacement. All right, first of all, synthesis. When you synthesize something, you're blending something together, you're merging something together, and that's all that's happening right here. we've got two different atoms, and they become unified together, not meshed, but still separate, but together as one compound. Here in synthesis. In decomposition, so if you think of decomposing, something rotting, it's coming apart, and it almost sounds like musical terms to me. We get coming together, like I should stop there, but I think of composing something as writing it down, and decomposing. Well, I guess I should have never gone there. Yeah, I don't have a good illustration with music at all. So decomposing is taking it apart, like you're rotting, food in the bottom of your compost bin. There you go. It's decomposing. It's coming apart. All right. Single replacement. This is just the flippity floppity of two in a within the formula. So what this is really referring to is on paper when you're writing down formulas of what's happening, and yes, you can actually make these things happen, like adding something to something that's already that's what that's relating to. But for right now, what they want you to be able to do is look at a like mathematical formula only of elements and compounds, which is what these are, and to figure out what's going on. So if you think of this as kind of like math, let's say this is the law of synthesis, this is the law of decomposition, this is the law of single replacement instead of the law of identity or something else. This is what these are, okay? So for this one, it's just the flippity flopping of these two atoms, okay? And so in the double replacement, that's really important to note that the same thing happens, but there's two compounds going on instead of a single element in a compound. So we have doubles down here, a single and a double up here, but it's just the flipping. Whoop, whoop. There they go. They just flipped. That's all that happened. So single replacement, double replacement. So if we were going to look at this on, where am I? In the student notebook on page 131, they ask this question: name the type of reaction for each of the following reactions equations. Let's start at the top. This synthesis is, you'll have to find it yourself to just know which one it is, but I'm copying it right out of the book, so it won't be hard. C plus 2H2, it becomes CH4. So that's a synthesis equation written down. And what this would look like in real life would be more like actually getting to play with chemistry, like we've been doing for our experiments in class. All right, so decomposition. Boop, boop, boop. Decomposition. It's like this one. 2NaCl. It becomes, notice, this was one element with one element. It becomes one compound. That's synthesis. And we've got one compound becoming 2N. Oh, that was nice. 2Na and Cl2. So if you saw this, you would know that that got broken up into two parts that were all here to begin with, and that's called decomposition. Okay? Now let's see what it looks like for single replacement in a real formula. We've got Ca, that's calcium, and we got is it dihydrogen? Dihydrochloride. All right. I'm not going to try to say all these because when the two's in front, I'm not positive. Lead learner here, not the expert, not I'm a mental health counselor, not a proper teacher of any of this. So we do classical conversations, and we are moms who are lead learners. So just a little make sure anybody who watches this knows. Just doing my best here. So what happens over here? Let's see what this looks like. We are on mixture of single replacement. Okay. I'm going to put it H2 plus CaCl2. So you can see that we've flip-flopped the A placement with the B placement right here. And we've got the 1 and the 2 together, the single element with the compound, single element with a compound that's flip-flopped 2 of the atoms. Double replacement, HCl and KOH becomes KCl and H2O. So see all the compounds? Compound. All right, so with that, there's one last. I told you there were 5. That's only 4, right? So let's look at the last one. It's my favorite. Combustion reaction is the chemical reaction in which a substance reacts rapidly with oxygen. That is the key word here. Often producing heat and light. So what is always a reactant in a combustion reaction? Oxygen. If you don't see oxygen, not H2O, no, just O. O2? I don't know. Oxygen. It's really just O. Yeah, because I'm getting there. If you see that, if you don't see that, how about this? If you don't see this, there's no way it can be combustion. All right, so let's look at some combustion examples. The Hindenburg blimp was a blimp. I wanted to read this to you because I thought it was really interesting. You should probably see the picture too, because it's just a fascinating and kind of devastating story. On its first trip to the U.S. from Germany, the Hindenburg had to travel through some stormy weather to reach its landing destination. The cause of the energy is unknown. I'm going to show you the picture. Some say static electricity built up, and others say lightning was the cause. Either way, the energy added to the hydrogen and oxygen gases, causing an explosive combustion reaction. So here is what happened in chemicals. In the formula here, we had hydrogen plus the oxygen. We get the water. It says hydrogen gas is the fuel needed for the combustion reaction to occur. When you burn your marshmallow contains many carbon, I'm going to see if I can see it here, and hydrogen atoms, which are common fuel for combustion reactions. Fossil fuels such as natural gas are composed of only carbon and hydrogen atoms, so are referred to as hydrocarbons. Hydrocarbons are often used as fuel in combustion reactions. If you use a lighter, like in this picture here, then it's most likely filled with butane, hydrocarbon butane, and the main component of natural gas is the hydrocarbon called methane. When methane has unlimited supply of oxygen, the following reaction occurs. Here we go. We got methane plus oxygen gas equals carbon dioxide and water. So what happens here? If carbon and oxygen are reactants and CO2 and H2O are products, you will know the reaction is a combustion reaction. So that's the ticket for that. So let's look at the example they have over here of combustion. I got it wrong. Look at that. We got all the answers. if you had your book out, you'd be able to write them down. I bet you do. So here we go. Carbon and hydrogen, and oxygen, and then we got to have the oxygen, right? And it says right here, if hydrocarbon, which is what that is right there, hydrocarbon, and oxygen are the reactants, which are on this side, and carbon dioxide, which we have right here, dioxide, carbon dioxide, and water are the products, then you will know it's combustion. So obviously I did not